Hey folks, welcome back to my YouTube channel. So today I will download a model from Hugging Face and I'll run it locally in my GPU machine. So a quick overview of what we have so far. So I have a Kubernetes cluster in which I have a single GPU node, and then I have a Grafana dashboard which will pull the matrix from the GPU node, and then we can see our utilization, memory, and so on. So before we go ahead into the practical implementation, let's briefly talk about what Hugging Face is, right? So actually, let me run, to have this set up, all you need to do is clone the repository here, which I've already done, git clone that particular repo. After that is done, then we need to run the run all command, which is in GPU Vast AI. It's in Kubernetes single node cluster setup, and then you will see a bunch of commands here. And then once you run the run all.sh, it will do all the tasks that we need to do to keep the Kubernetes cluster up and running. So let's talk about Hugging Face in the meantime. So think of Hugging Face like a GitHub for pre-trained open source AI models. So once you click on models, you will see all the models that are available. A couple of things you need to filter out. Right now, I'm only interested on text generation models, so I'll click on that. The architecture that I need would be transformers, and then there are other filters here, so I'll go ahead and click most downloads, and then you will see the most downloaded open source models, and you can use this locally, right? So for my particular use case, the model that I will use today is going to be the Llama model by Meta, which is 3 billion parameters. So one rule of thumb, right? So essentially what happens is if you have a 3 billion model, you can multiply it by 2, and then you can think that's the model of the size. So it might not be accurate 100% of the time, but that's generally what it teaches, right? So in our case, it's 3 billion parameters, so it should be 6 gigs, right? So let's have a look here. We see one file is 5 gigs, another file is 1.46, so it's roughly 6.5 gigs. So that gives an idea to us about what's the size of the model weights, right? So, and the file that ends with .ceph tensors are the model weights. So, and while this is being installed, there are a couple of things that I would like to address today. So let's talk about transformers in a bit. So, transformers are a type of neural network architecture that handles data like text, audio, images in a sequential order. So, for example, if we have a text that says the cat sat on the mat, right? So in transformer architecture, it would understand the word in a sequential way. Instead of understanding just one particular line, like they or the cat or sat, it will understand the entire context of the line, and it will understand it one by one in a sequential fashion. So in this situation, it is aware of the context that a cat is sitting on the mat. So that's essentially what the transformer architecture is from a high level, but I'm pretty sure there are much better videos out there and great books that you can read on about transformer architecture, where things would be explained in much more detail. So after we have the model downloaded locally in our machine, so we will write a Python code which will, load the model into our VRAM, and then GPU will use it, right? So when I run model.to cuda, so we know cuda is the software stack that was built by NVIDIA to interact with GPU machines, and then PyTorch is a framework that sits on top of CUDA. So PyTorch will copy all of the model weight. So the model weight in this particular situation is these two files, .ceph tensors files, which is 3 billion times 2, 6 gigs roughly. So it will it will pull all the model weight from system RAM to the VRAM, and GPU can only access data in VRAM, right? Because when we download this particular model, it will be in our disk from and then from the disk it will be pulled into our system memory, and from system memory it will be pushed to our VRAM. So that's the flow essentially. And then performance is best when all weight sits in the VRAM, right? And each Ceph tensor is a chunk of model weight. So we see two Ceph tensors file, two chunks of model, and then we see that if the model weight will fit in the VRAM, then performance is going to be best. So if we look at our Vach.ai, we see that the GPU instance that I'm renting is 16 gigs, and then the model that I'm trying to run is just 6 gigs, right? So it will perfectly fit in my VRAM, and then I will get a good performance out of it. So what are weights, right? What exactly are these two files that we see here? So weights are learned logic during training. So when that model was trained, and all the logic that it came up with is in these two particular files. And When we use the learn logic to answer a question, the model also needs a temporary scratch pad to do the math. That's what activation and KV caches are, right? So these two things are quite important as well. And then the reason I'm talking about activation and KV caches is because these two things will sit in our VRAM as well. So from a high level, weights are permanently learned models knowledge, which we see there. And then activations are temporary results produced while computing each layer. KV cache would be memory of all previous tokens, so we don't need to compute on each step, right? So tokens are the query parameters that we send to the model. So for an example, in a text-based model, let's say if it's a 50-word sentence, then it's 50 tokens. To store that, it might take 200 MB cache space. If the token size is 2000, it might take 2.3 gigs, right? So essentially, if the number of token increases, the memory consumption by KV cache increases also. So if we have a 12 gigs VRAM, then let's assume 9 gigs is the model weight, 1 gig might be used by activation, 1 to 2 gigs might be used by KV cache. This is an assumption, right? But that's essentially the flow. So to understand this in a practical way, let's take this example. So think of model like a person who is doing a simplification, right? So that's the user query that we get. So do a simplification of that. So weights, these two files that, right? So .saved answers files. So weights is what we have memorized so far, like multiplication, addition, simplification rules, and so on, what I was trained on. So I was trained in a bunch of mathematical operations. I know what different operations do. I know the value of the numbers, and I know how to work on those numbers. So that's my weight. Maybe I might have not given that data during my training, but based on all of the trainings that I've done, I know how I can calculate that. But for me to calculate that, I need to use some memory where I can use that as a scratch pad, right? So that's where activation would be. Here I'll do things like, okay, for me to find the total answer of that, at first I need to add 5 plus 3. So 5 plus 3 is going to be 8. And then I need to do 8 times 2 and so on. So that particular logic or that calculation, it's stored in VRAM as well, right? So that is used by the model as its scratch pad, where it kind of makes note of its things, right? So, and then it slowly moves on and does the calculation. But then KV cache comes into place where it does this first calculation. 5 plus 3 is 8. Then it will store the 8 in KV cache. So we don't need to redo the earlier steps, right? We already have the result from our earlier step here. And then when we move on to the second calculation, let's say 8 times 2, we know that 8 was already calculated, so it's in our KV cache. 8 times 2 is 16, so we already have 16 from here so far. And then we'll move on, so we need a scratch pad again, so we need to see, okay, what do I need to add now? Before this, I know it's 16 because it's in my KV cache. The next thing I need to do is 16 plus 10, so that would be 26, right? So now we'll store that 26 in our KV cache again. So we go to the next operation, and then the model will see that, oh, I need to do minus 6, but what do I need to do minus 6 on? Then it goes to the KV cache, and then it goes, oh yeah, I have 26 stored before, so I need to do 26 minus 6, and then it comes to 20. And then the same logic, right? So now it'll go in a sequential way because it's a transformer model, right? So it'll go 20 times 2, and then how does it get 20? Well, it's in the KV cache, so 20 by 2 is 10. So essentially that's how the computation would go on, and that's how these different aspects are used in the VRAM. So if you have a model that is 12 gigs and then you have a 12 gigs of VRAM, you might not get the best efficiency. Essentially what happens is, say if you use too much, like if your VRAM overflows, right, then PyTorch may offload some of the layer or caches to CPU RAM. If that feature is enabled, if offloading is enabled, it will be offloaded to CPU RAM. If that is not enabled, then you will encounter errors like cuda out of memory. But offloading is not necessarily the best thing to do as well, because the drop in performance is going to be insane, right? So we need to I think from my understanding so far, like we need to kind of have a model that fits this criteria so that we efficiently use our memory. Okay, so my installation has completed on the screen in the right. So let's go ahead and let's complete my task. So let me copy this part here. Okay, so my pen is completed, and then let me go ahead and let me configure the Grafana part as well. So okay, it installed a bunch of libraries here, right? So, you know, in a Python virtual environment. So now we should be able to go ahead and use all of these libraries. And then for my Grafana dashboard to be up, I need to map my local port 3000 with remote port 80. But before I do that, I need to run our service monitor file. So the service monitor will help us export all of our GPU matrix. So all I need to do is kubectl apply -f service monitor, and then I will just make sure all of my pods are running. So yeah, it looks running. Or the other command to get that would be to just go grep -v and then filter for running. So we're saying give me everything that is not running. In this case it goes completed. Yep, we're happy with that. Cuda validator. So now let's go ahead and connect on the port 3000 to get our Grafana dashboard. SSH, and then all I need to do is, okay, let me actually go to fast.ai. Let me see the connect option. Let's copy that, and then okay, so remote port 80, local port is going to be 3000, and I'm connected. Okay, so now I should be able to load my Grafana dashboard in my localhost environment. Okay, localhost 3000. So let me just close that. Okay, I have my Grafana dashboard loaded, and you will see that we have the file here as well. So if I go back to my parent directory, there's a dashboard we have in Grafana. So you can go to Grafana and you can see that there's this file gpu-dash.json. So once you have your Grafana loaded, all you need to do is click on the plus icon, new dashboard, and then we are going to import the dashboard. So we'll discard and then click there. That's the GPU dash, select, import. So these are the metrics that I'm trying to monitor: GPU utilization, free memory, some clock frequency, and so on, right? So once we run it, we'll get more data. Let's go last 5 minutes. So you know, and then this data export only started once we created that service monitor, right? So once I'm here, what I need to do is I need to go to my Python scripts. So for me, before I download this model, this is a gated model, so I need to authenticate myself. So if you're downloading in gated model, just make sure you accept the terms and conditions, and then it will take some time, but you will get the approval to use the model. So before I do that, I need to authenticate myself. So it will be hit f-auth login. It'll ask for my token, which you can create from the user portal. So let me go ahead and paste my token here. Add token as get credentials. Nope, I don't want that. So the current token is active and I can download the model. So for me to download the model, all I need to do is to click on that part, click on clone repository, and then copy the CLI version. And let me just paste that here. Before I paste that, I kind of want to download it as my local directory. So to do that, what you can do is you can go to the Python scripts, and then you can just cat on the huggingface.txt file. So, you know, whatever model you copy, you can just mention this flag here, local directory, and then give the path. So that way you can run your model. Let me just copy that now. Okay, and then let's go ahead. So yeah, folks, the model has been downloaded completely. We can see that was the total file we downloaded. So all the files that are listed here are here. So again, just click on the three dots, clone repository, make sure you have Hugging Face CLI installed, and then just copy that. If you need to save it to any particular local directory, just give the path, right? So now let me have a look here, and then I can see my models is installed. And then I have my test model.py file here as well. So let me print my working directory. So it's that particular directory. And I need to make change in this particular file here, test model. I just need to make sure that my model directory is what I have here. And then, so root vast AI, and it's actually Python scripts. Okay, so let me just go here. And then just change the path. Essentially, this is what we're saying, that this is where my model is. Python scripts and models. So we see models. Once we go to models, we see it's metal at 3 billion. Okay, yep, that's correct. So after we do that, let me just save this file and let's do a cat on this file as well, and let's understand what we're doing, right? So cat test. Okay, just need to go back. So essentially what I'm doing here is using that particular model. I'm saying that you're a helpful assistant. That is my query. In one paragraph, explain VRAM uses for LLMs, weights, activations, KV cast in simpler terms. So now let's run the Python code, Python 3, and then test model py. So let's have a look in our Grafana dashboard as well, right? See, our GPU temperature is quite stable. It's around 49. Utilization is around 0% as well. And then all of these things are quite stable and normal, right? But there we go. As soon as we executed this code, now the model is doing its thing, right? We see the GPU temperature has gone up. And then, okay, now we got the response from our AI model. So it says that, imagine your brain is a massive library with infinite number of books. Each book represents a word, a token from the input text. The more books you have, the more storage space you need. In the context of LLMs, we use 3 main types of memory to store these books, right? So we've already discussed about this, but let's see what we used here. So there we go. Our GPU utilization went up when we ran this model. Our GPU temperature went up as well. The SM clock frequency, free memory went down all the way to 9.61 gigs, and then our memory used went up to 6.19 gigs, right? So this is what I was talking about when I was saying that be careful about the model weight that you use and then the amount of VRAM that you have. In my case, my VRAM in total is 16 gigs, right? So we can see that information here as well. So let's run a bash loop here. So let's go while true do sleep for 2 seconds, and then all we want to do is run NVIDIA hyphen SMI and then be done. So in the meantime, let's actually change our model.py as well, so we'll prompt it for something different. So let's just go here and then okay, so in one paragraph, or let me actually give me a travel itinerary to Vietnam and Australia for 14 days. So now we've just changed our query, and then let's see, while we run this, let's actually run our NVIDIA hyphen SMI as well. So while true, okay, do sleep to NVIDIA hyphen SMI done. Okay, so a couple of things before we run the model, right? We see GPU utilization is 0%. Our current memory is 2 megabits. Temperature is quite normal as well. So now let's, and we see something similar in our Grafana dashboard too, right? You will see that information come up here first because, here we're talking directly with the kernel, but on the dashboard, a couple of things need to happen before that matrix is pulled over here. So let's go ahead and run them up. Let's go ahead and run the model, and then let's see the utilization going up, right? So remember, we have a 6 billion token model. So the max memory that it will use will not be more than 6 gigs, right? Because, and on top of that, the activation and the KV cache space, right? So our context is quite small, so we're not using a lot of KV cache. And then, say the model fits in perfectly in the memory as well, because we have more than enough memory. And this is the prompt, this is the response we got from our model. So tier 1 to 4, Hanoi in Vietnam, and then Blue Mountains, and then go to Sydney and all that. So here, let's see. So that dropped because the model was not being used. And now let's do a refresh again. So let's give it a couple of seconds. Let me just run it one more time. And there we go. So that spike is from the previous run, right? So we see, utilization dropped, but then the temperature got increased, SM clock frequency increased. We'll see the utilization matrix going up as well. So let's just refresh. Okay, so we see this here, right? In NVIDIA hyphen SMI, it's quite fast, but then it takes a bit to be loaded in the dashboard. Okay, and then here we see the GPU utilization going up a little bit, but it wasn't that much because it was not a complicated query, right? So, but we see the memory utilization been going up, and then we see the frequency, the free memory dropped, and so on. So yeah, thank you for watching this video, guys. And to sum up, we downloaded a model from Hugging Face. We ran locally in our own machine. We understood a bit about how VRAM works, how we load the model. We played around with a transformer model, understood about model weights, and then we saw the GPU utilization in our Grafana dashboard. Thank you so much for watching.